Right, so the topic for today is how shit works storage, because the assumption here is that knowing how shit works makes you better software engineers, and that's what this is all about. So, as with all good stories, we're going to start with a question. So, I'm going to show you a graph. This is a New Relic graph from one of our production services running in production. I took that maybe a week ago. And the question is, what is wrong with this picture? Now, obviously, this is way, way, way too detailed, so you can't see it. Let me zoom in a little bit. This is just one sample, random sample from this entire graph. This graph shows 7 days of just database queries, right? One of our production services showing the query in the hot path, the one that happens like 99% of the time against the database. And while it is probably a little bit too small, you would have been able to see that our average query latency is about 3 milliseconds, right? 2.5 to 3 milliseconds, which is pretty good. That's a well-tuned MySQL server. I'll clue you in. There's a minimum query latency of about 0.2 milliseconds, which is really good, and a maximum latency of about 10.2 seconds. That is not milliseconds, that is seconds. So we have a 4 orders of magnitude difference between our minimum query latency and our maximum query latency. And obviously, when you see something like this happen in production, the obvious question would be, what the hell happened? Okay, so let me right off the bat skip a beat and eliminate a bunch of questions, right? So this is not a trick question. There are no server misconfigurations or some horrible code bugs or some cron job running. That is not the point of the exercise, right? This is a properly tuned, properly operated server running in production that everyone is largely happy with, and its 99.99 percentile latency is just terrible, right? It's 10 seconds. So obviously the question is, what else sucks here, right? What else could go wrong? Now, in order to set the stage, right, the one thing we need to do is debunk a common myth that is acceptable to most software engineers. And that myth is I/O is simple, right? You open a file, you write to the file, you flush if you're advanced. If you're not advanced, you just close the file, and the file goes onto the hard drive, right? That is the abstraction that you know coding in Java or Node or whatever. That is a lie. And the reason that it's a lie is, if we zoom in just a tiny, tiny little bit, we can see that in reality, things happen to be a lot more complex, right? So we have our application writing file through a whole stack of stuff running in kernel space, and things end up on the hard drive. So you have your virtual file system, you have your actual file system. On Linux, the default is ext4, which is a pretty good file system. All of that is running on top of a logical volume manager that manages the various volumes, RAID volumes and stuff that you have. You have your I/O scheduler, and then you have your SCSI driver stack, and the whole thing is completely hidden away from you behind this nice abstraction that is called java.io.file input stream whatnot. The reality of it is that if we zoom in just a little bit further, it actually gets a hell of a lot more complicated. So everything that was in kernel space in the previous slide is actually just this, the storage subsystem within the kernel. But then you also have your system bus drivers, and you have a whole layer, a whole stack of abstractions sitting between your very, very simple file I/O API and the hard drive. Because once you leave kernel space, you actually have the hardware. And the hardware is also layered in layers upon layers of abstractions. You have your PCI Express bus, that speaks to the serial ATA drive controller, that talks to the hard drive. And I was too lazy, so I didn't put together a slide zooming in onto the hard drive and showing just how complicated things get, just in terms of, how many moving pieces are on the way between your file handle and the hard drive. So the takeaway here is that I/O is what I call the onion of abstraction, right? You have or parfait, if you will, but I prefer onions. So you have these layers upon layers upon layers of abstraction, and the whole point of these abstractions is to hide away a hell of a lot of complexity from you, the software developer, so that you can do your job efficiently. Because if you had to, just scrolling back a little bit, If you had to know these things and you had to talk to each and every one of them just to get a file on disk, you wouldn't get anything done. And that is why software was so damn hard to write in the 50s, 60s, 70s, 80s, 90s, and it's still hard today because we're still building abstractions on top of abstractions just to make it simple. So, the thing about abstractions is that sometimes if you're not careful, they tend to leak. So, it is known that sequential access is fast, whereas random access is slow, right? Everyone knows that. You shouldn't do file seeks and jump around on a hard drive. So obviously the question is, so what, or why? Why should you care? Why should you care is, just one example of it is from the MySQL reference manual. And because this is a lot of text and it's white on black and you can't really read it, and it's not that interesting, I've taken the liberty of highlighting a few keywords here. Disk seeks, blah, blah, performance bottleneck, blah, 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 one disk seek to read, right? So at a minimum, you're doing one physical disk seek per every query that you're running against the database. And that is like the best case scenario, assuming, of course, it's not everything hot in memory. And the question is, why are disk seeks such a huge deal, right? Why is that the problem? Why is that the bottleneck? And the reason is this, right? This is a pretty damn outdated diagram of a hard drive, but it's the best I could find in short notice. It shows kind of a rough abstraction of what a hard drive looks like on the inside. So you have your magnetic platter, because everyone knows that hard drives are just these weird rotating disks with like magnetic surfaces on them. And that is one of the two things that you really need to know. You have a rotating magnetic platter, and you have this thing called the read head, or the read head sits on the actuator arm, blah, 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 blah. There is a physical device that is hovering on top of your physically rotating magnetic platter that reads data off the disk. And that gets involved every time you run a query against your database. Right? So that is a physical medium. And physical media, mechanical media, has certain attributes that can affect your day-to-day. So the first thing to take into account is something called rotational latency. So this is a very simplified diagram of what happens when you actually want to read a bit of data off of the disk. This is your read head, right? There's this tiny, tiny thing hovering just like a micrometer on top of your, over your physical medium, your physical magnetic platter. And you have a bit of data situated somewhere on the disk that you actually need to read. Now, the first thing that happens is a read a read command is issued to the hard drive. The first thing it needs to do is, because data can be in any radius from the center of the drive, it physically needs to move the read head to the correct position in order to read your data. So that's the first thing that happens. That is what is commonly referred to as seek time. Now, in effect, when people say seek time, right, when documentation mentions disk seeks, it doesn't only include the length of time that it takes to actually move the read head, because it moves linearly, right? It's stuck on a single arm and it just moves like this. So it doesn't take a whole lot of time. But once it's moved into position, you have the second phase, which is waiting for the data to actually show up, rotate into place underneath the read head. And that is what is called rotational latency. Now, once the data is in the correct position, there is a certain length of time that it takes to actually read the data off of the physical medium. And that is called transfer time. So all of these things put together is the length of time it takes when you issue a read, even if it's just 1 byte, right? You need to read just 1 byte off of a disk. That is what needs to happen. The second thing that comes into play is throughput. So we've said that once the read head is in place, there's a certain length of time that it takes to actually read data off of the disk. So if you understand latency, let's discuss throughput. And throughput depends on two factors. The first is called areal density, and it's not really that complicated a word, right? It comes from area. There's an area on the physical hard drive, and there's a density of data built into that particular area on the drive. So that is the areal density. And the second thing that comes into play is Newtonian physics, which is kind of unfortunate, but we'll get to that in a sec. So areal density, you don't really need to dig into this too much, but the fact of the matter is that as drives evolved over the last 60 or so years, a lot of effort, a lot of research went into increasing the bit density of data on the hard drive, right? Because hard drives today are, nowadays you can buy a hard drive with like 2, 3, 8 terabytes of storage, and it takes roughly the same size as a hard drive with 20 gigabytes from maybe 15 years ago, right? It's the same physical size. So something had to change to support that extra capacity. And that something is called areal density. You can stick more bits into the same surface area on the physical platter, on the physical medium, right? So that's one thing that comes into play. Now, in order to explain the other thing that is surprising in this whole, this whole shenanigan of actually reading data off of a rotating platter, we need to dig a little bit into math. And don't worry about it. It's not going to be much math or hard math. The thing to note is rotation is fixed, right? Your magnetic platter rotates at a fixed velocity. Typically, 5,400 to 15,000 rounds per minute, right? So there's a certain rotational velocity that is constant. That is called constant angular velocity, or CAV. Now, Newtonian physics tells us that the linear velocity, that is, basically the span that the read head travels in a given cycle, is the angular velocity times the radius. Now, you don't really need to understand the math behind it. The punchline is that throughput changes over the course of the physical medium. You don't get the same throughput from the inner section closer to the center of the hard drive that you do on the outside of the hard drive. And that is actually very easy to understand, because if you drive a car, you know that you need to rotate your wheel a varying degree, depending on if you're on the left lane or on the right lane while doing the turn, right? It's not the same, you don't travel the same distance within that turn, right? So that's the intuition behind why throughput changes over the course of the disk. So for instance, if you're building a video streaming application, right? You're doing only sequential access, everything is fine. You're just reading data off of the hard drive as fast as you can. You're still gonna be seeing different numbers throughout the disk. So this graph here, which I'm sorry to say is a bit too dark to actually read out, what you should focus on is the blue line. And that shows the read throughput throughout the span of the hard drive. This is a 6 terabyte hard drive. So from the beginning to the end of the hard drive, because these things are generally recorded outside in, the throughput decreases. And this is a fully modern, just a brand new hard drive that's been taken out of the package, stuck into a computer, and had the benchmark run on it, right? So the throughput that you get is not consistent across the hard drive. So that is how an abstraction leaks, right? You assume certain things about the performance of your storage subsystem, and there are subtleties there. And it's not a small difference, right? You get 200 megabytes at the outside, and you get maybe 100 on the inside. That's a 50% performance decrease, right? That's something you need to realize. Commodity drives today are available typically in either 5,400 RPM, which is revolutions per minute, right? That's the number of times that the physical medium spins in a minute. Most commodity hard drives that you buy in the store, whether for desktops or servers, tend to be of the 7,200 RPM variety. I don't know why that particular number, but it's been around for 20 years and it's very consistent. So what does that mean for latency in effect, right? How long is a disk seek? So if you take this number, the 7,200, and you want to know how many times per second the disk rotates, you just divide it by 60. So you get 120 revolutions per second. And then you want to know, well, how long does it take? Like, what is the worst case scenario if my read head is in position and I issue a command and it has to wait for the platter to rotate fully? How long would that take? So you just take 1 second, divide it by 120, and you get back 8.33 milliseconds, right? 8.3 milliseconds is a long time in computer time, right? That is a physical disk seek. That means that if you go to disk in your service, the best you can expect out of commodity hardware is this number. So if you go to disk, right, the best case scenario, which is implausible, is that the read head just happens to be right on top of the data that you want to read. You know when that happens? When you do sequential reads, right? If you read data sequentially, that is the best case scenario. That is beautiful. but you don't typically do that. So if you do any sort of real-life workload, you're going to run into numbers or in this ballpark, right? 8 milliseconds is a long time. If you benchmark our services at Wix, you're going to find that most of them, are in the 20 millisecond range, 10 milliseconds. Some of them are 2, some of them are 200, depending on what they do, right? That is typically, if it's below 10 milliseconds, that means that you're not going to disk. That's a computational workload. That's what you should aspire to. So this is why you should strive to never, ever, ever go to disk if you can avoid it. And what does it mean in practice, right? Let's look at actual factual numbers. So with a modern hard drive, you get about 200 megabytes per second read throughput if you do sequential reads, right? You read a video file off of disk, this is kind of the performance that you can expect. It can be a little bit less, can be a little bit more, but that is the ballpark. But you get around 300 I/O operations per second, which is a bit of a vague concept, but in practical terms, if you do fully random reads off of your hard drive, you're going to get 300 requests satisfied per second, which is unfortunately just not very much, right? So with a typical 4K block size, which is the minimum amount that a drive that a read head will actually read off of the drive, in practice, if you do pure random access, you get 1.2 megabytes per second. That is not gigabytes. That is not 100 megabytes. That is 1.2 megabytes per second if you do pure reads. And 1.2 megabytes per second is crap, right? It's very, very little performance. If you if you do not tune your databases properly, for instance, you're going to run into this. Your databases are going to crawl, your services are going to stall, your customers are going to leave you, and you're going to go bankrupt and have to live in a street somewhere. I have been told that it is good practice to either start or end your lecture with a quote, a citata, as our venerable member of parliament said just recently. Right? So this is Shakespeare, which makes me look smart. I'm not. In practice, what can we do about it, right? So now that you know just a tiny little bit about how mechanical hard drives work, here's a bit of common sense about what you can actually do to tune your services to get proper performance out of your storage subsystem. So the first thing you can do, pretty much on the software side, is fine-tuning. Obviously, you can add more RAM to your. I'm gonna continue with the database example because it's something that is easy to relate to, right? Pretty much everyone here writing a server has a database, typically MySQL, but the same applies to MongoDB or any other storage technology that you can think of. So the first thing you can do is provision more RAM. You have more RAM, you have more caches, you need to go to disk less often. Good for you. If you can stick your entire working data set in RAM, maybe you don't need to go to disk ever. And RAM is way faster. RAM is like nanoseconds, right? A few dozens of nanoseconds, but that is still like 5 orders of magnitude better than you get off of a mechanical hard drive. The second thing you can do is you can take into account that mechanical hard drives are slow, and you can do something about it, right? You can carefully adjust your indices. You can carefully adjust your data that is actually kept on disk to either minimize random reads. That is what databases do, right? Most modern databases employ one of several data structures, typically a B+tree, designed to minimize random read access to the drive. That is exactly what they're there for. And that is the inherent complexity in writing a proper database. So you can, even with a typical workload, like Wix server workload on top of MySQL, there are still things you can do. One thing is, if, for instance, you have IP addresses in your database, especially ones that you index by, typically what you would do naively is you would say, well, I have an IP address, I'll just render it into a string and use that. Okay, and then you have 4 3-digit numbers with dots. It's 15 characters, right? But IPv4, obviously, IPv4 addresses are just unsigned bytes. They're 32 bits. That's all you need, right? So you can use unsigned ints. Now, this very, very simple change reduces 75% of your index size, right? That is a huge win. That means that MySQL needs to seek less. It can store more of the index in RAM. It can, it can cache your data more efficiently. It doesn't need to go to disk that often. So just this, not only is this a reduction in size, which means you may need less storage, it also actually has the potential of improving your runtime performance. A second thing that you can do, which is something that I think someone mentioned on our Wix Engineering Slack channel recently, Percona has a very, very famous blog post that deals with how to represent UUIDs or GUIDs, as they're more commonly known, in databases, that not only improves performance, like query performance, but it actually reduces your index size by about 30%, which is huge. Now consider that in a web scale system like Wix, when you do sharding and when you avoid foreign keys and that sort of thing, you would actually very, very often use unique IDs as primary keys. So a 30% reduction, right? If you're saving 70 million IDs just to map, Wix site ID to, to a URL or whatever it is you do, you've just saved 30% off of 70 million UUIDs, which is a pretty big saving, right? So these are the sort of techniques that you can employ on the software side to actually improve your performance, go to diskless, save yourselves some performance headaches. The other thing you can do on the hardware side is use a sledgehammer. So RAID level 0, which is called RAID striping, essentially what it does is it takes a logical disk, right, a logical volume in your file system, and it just spreads it across multiple drives. Now it doesn't do so, there's a different mode of operation called JBOD, which is just a bunch of disks, where it just takes hard drives and concatenates them to present them as a bigger hard drive. That is not the case here. What striping does is it takes blocks of data and it randomly distributes them among multiple physical disks. With the idea is if data is evenly distributed among multiple disks, then you get multiple read heads and multiple physically rotating spindles, right? So you can get basically a linear increase in IOPS, a linear multiplication of the number of disks you have with the 300 I/O operations per second that you get off of a mechanical hard drive. Win, right? You've increased your random read throughput. Beautiful. Now, if this technique sounds vaguely familiar, it is. In software development, we just call it sharding or partitioning. It's the same concept applied to a different notion. It's just a hardware level partitioning of data on your hard drives. One thing to remember if you go this route is that abstractions break at every level, right? It turtles all the way down. So don't just go ahead and implement RAID 0 in your actual production systems, because RAID 0 isn't practical, it's dangerous. I'm practically done now. It's dangerous. If you have multiple spinning hard drives, mechanical hard drives are prone to failure because they have moving parts, and moving parts, as anyone who owns a car knows, tend to break over time, right? So that means you're increasing the probability of a hard drive failure by the number of hard drives you have. And crucially, if you just distribute data randomly on top of multiple hard drives and one fails, you've lost one nth of your data, where n is the number of hard drives that you have. So RAID 0 is not a practical solution. So you might think, okay, I have RAID 5, which is striping RAID 0 with parity. The thing about RAID 5 is it might be slow for your workload. So that is not something you want to go into lightly. RAID 10, which is basically a mirrored array of stripes, is expensive because you need to provision twice as many hard drives, but you get really, really good performance and safety out of that. Do you have the money? Like, is it worthwhile? Do you need the performance that it gives you and the durability that it gives you? I don't know. That depends on your use case. So, in summary, do your homework and benchmark, right? If you want to know how your system behaves and how to tune it better, the more you understand about the underlying mechanics of your software and hardware stack, the more effective you're going to be as a software engineer. And with that, if there are any questions, I'm spent.